This is an exponentials and logarithms question. Give it a go first, see how far you get. If you get stuck on anything, then just skip through the video to see my hints for each part. So for part A, populations P1 and P2 of two bacterial cultures T hours after a certain instant are modeled by the following equations. So we're given P1, 1600 e to the quarter t, and then we are given P2, 100 e to the half t. Told that t is a real number and that it is bigger than or equal to 0. And we're told that when t is equal to capital T, P1 contains 4,800 more bacteria than P2. And we want to find, in terms of natural logs, the possible values of t. So then what you want to do is, for part A, the hint is to get this as an equation involving P1, P2, and 4,800. And once you have that equation, then you want to use what we have for P1 and P2. Once you've put those two into the equation, or combine them all together, you will have a quadratic. A hidden quadratic, so you have to then think about how do you solve it, what substitution do you make to solve for t. So this equation here is the same thing as saying P1 minus P2. So P1 contains 4,800 more bacteria than P2. That means that P1 minus P2 is equal to 4,800. And then we can replace P1 and P2 with the exponential things that we had in the beginning of the question. So 1600 e to the quarter t. I'm actually going to replace this now with capital T because the time is capital T, as it says that. And then this minus P2, which is 100 e to the half capital T, is equal to 4,800. So this is a hidden quadratic. I'm just going to rearrange it so it's easier to see how that is the case. I'm going to bring everything, move these two terms to the right-hand side, bring the 100 to be first, then it'll be minus 1600 e to the quarter t, and that's plus 4,800. So remember, I've moved everything, I've moved these two terms to the right-hand side, and then this is equal to 0. I'll then divide everything by 100 to simplify it. E to the half t minus 16 e to the quarter t plus 48 is equal to 0. So you might now see how this is a hidden quadratic. So if we were to consider e to the power of a half t, this is the same thing as e to the quarter t times 2, so that's the power. And if these two things are multiplied together, we can then rewrite this as e to the quarter t, all of that, squared. So then our equation becomes e to the quarter t, all squared, minus 16 e to the quarter t plus 48 equals 0. And we could rewrite this, we can let x equal e to the quarter t to make things a bit neater, easier to see how exactly we're going to factorize this as well. And then we get this. And then we can factorize. So the two factors, or the two things that times together to give 48 and add to give minus 16, would be minus 12 and minus 4. That's equal to 0. So we get x is 4 and we get x is 12. And then x is e to the quarter t. So e to the quarter t is 4 and is 12. We can then do natural logs of both sides. That gets rid of the e. Right hand side becomes ln 4. Same thing here. Natural logs of both sides. Gets rid of the e. Right hand side becomes ln 12. And then we can rearrange. So t then becomes 4 ln 4 and also 4 ln 12. And that is our answer then for part A. Okay, so on to part B, determine the greatest value of P. So it says, at a certain time, there are P extra bacteria in P1 compared to P2. Determine the greatest value of P. So All right, how are we going to break this down? First of all, you want to get an equation for this. So what's a way that we can represent what we have there? Once you have that equation, so it'll be P in terms of P1 and P2, you can then use the stuff that we have up here to then replace the P1 and P2 with some kind of function of time. So we'll then get an equation for P, which is a function of time, which has those exponentials in there. And then so once you have that equation, we then need to think about how can we get the greatest value of P. So greatest value means we're trying to maximize P. We're trying to make P as big as possible. Whenever you're trying to maximize or minimize a function, then you want to think about what operation can you do to the equation to work out what the maximum or minimum value would be. So maximizing or minimizing a function means we have to differentiate. So that's what we're going to have to do. So let's first set up that equation. So for part B, we have P extra bacteria in P1 compared to P2. So that means that P1 minus P2 is equal to P. And then we know that P1 is 1600 e to the quarter t, P2 is 100 e to the half t. Oh, and there should be lowercase t as well. So this is what P is equal to. So then once we have that equation, we can then differentiate both sides. So we find out dp dt. So the quarter comes out when we differentiate. A quarter times 1600 would be 400. So that becomes 400 e to the quarter t. Half comes out when we differentiate this. Half times 100 would be 50. So this becomes minus 50 e to the half t. And if we're trying to find a maximum, we'd set this equal to 0. So now we're solving this equation. I'll bring the 50 stuff to the right-hand side, so we get 400 e to the quarter t is equal to 50 e to the half t. And then we can divide both sides by 50. We end up with 8 is equal to, or rather, 8e to the quarter t is equal to e to the half t. And then to solve this equation, I think the best thing to do would be to combine these two exponentials together. So then we can divide both sides by e to the quarter t, and we end up with e to the half t over e to the quarter t is equal to 8. And the left-hand side, we can use the rule that if we have a to the power of x all over a to the power of y, then this is the same thing as a to the power of x minus y. So then this becomes e to the half t minus a quarter t is equal to 8. Half minus a quarter is a quarter, so e to the quarter t is equal to 8. And then we can do ln of both sides. So we get a quarter t is ln 8. T is then 4 ln 8. Okay, so we're getting somewhere. We're not quite done yet. The question is asking for the greatest value of P. So we've just figured out a value of T. So we can then put this into this equation to then work out what P is. But before we do that, we should probably first check to see if this actually corresponds to a maximum or if it is a minimum. So we'd have to then double differentiate. So we have dp dt. We can then work out d squared p dt squared. So double differentiate this equation that we have up here. And we end up with, so quarter comes out, quarter times 400 is 100. Take the half out, becomes 25. So then we have our double differential. And then what we do is we can put in our t value. So put in t is equal to 4 ln 8. We could just do this in our calculator, but I'm going to do it manually just so you can see how it works. So 100 e to the quarter times 4 ln 8. We'll go over a few different rules in doing it this way, so I thought it might be useful to do it manually. Okay, so the first term becomes 100 the quarter and the 4 here cancel out, and then we are left with ln 8, e to the power of ln 8, and this second term becomes 25, so e to the power of, so a half and the 4 become 2, so it becomes e to the power of 2 ln 8, and that second term we can then write as, so I can bring the 2 up as a power of 8. So because it's in front of the ln, I can bring it up as a power. So it becomes 25 e to the power of ln 8 squared. And 8 squared is just 64. The reason I did that is because now the e's and the ln's can just cancel out. We couldn't do that before when the 2 is in front. So it has to be, the rule is that it has to be e to the power of ln x is equal to x. If there's some kind of number in front, like 2 let's say, then this isn't the same thing as 2x. It would in fact be x squared, because e to the power of 2 ln x is the same thing as e to the ln x squared. And then the e and the ln cancel and you're left with this. So then what we have here becomes 100, or rather the e and the ln cancel. This is 100 times 8. This would be 25 times 8 squared. And when you work this out, this gives you minus 800. So we know that the double differential is negative when you put in t is equal to 4 ln 8. And that means this is a local maximum. Negative means that the gradient is decreasing. And if you think about a maximum, as you go across from left to right and draw successive tangents, you see that the gradient is getting shallower and shallower and shallower, or more and more negative from its initial positive value. So gradient is decreasing. Double differential tells you the rate of change of the gradient. So if our gradient is decreasing as we go from left to right, the rate of change of gradient should be negative, which is what we have at a local maximum. So then that means that the 4 ln 8 is correct. That is the value of time that we want to be using. We can then put that into our population equation to then work out what p is. So on to the final part now. So population from before was 1600 e to the quarter t minus 100 e to the half t. And then we can put in t is equal to 4 ln 8 into this. So put in t is equal to 4 ln 8. I don't think I'll do this manually this time. I'll just put it straight to my calculator. And then we end up with population is 6,400. And that is our answer.